Tutorial 15, Navigation. This lesson provides an introduction to cross-country flying under Visual Flight Rules, VFR. It contains practical information for planning and executing cross-country flights for the beginning pilot. Air navigation is the process of piloting an aircraft from one geographic position to another while monitoring one's position as the flight progresses. It introduces the need for planning, which includes plotting the course on an aeronautical chart, selecting checkpoints, measuring distances, obtaining pertinent weather information, and computing flight time, headings, and fuel requirements. The methods used in this chapter include pilotage, navigating by reference to visual landmarks, dead reckoning, computations of direction and distance from a known position, and radio navigation by use of radio aids. An aeronautical chart is the roadmap for a pilot flying under VFR. The chart provides information which allows pilots to track their position and provides available information which enhances safety. The three aeronautical charts used by VFR pilots are sectional, VFR terminal area, and world aeronautical. Sectional charts are the most common charts used by pilots today. The charts have a scale of 1 to 500,000. 1 inch equals 6.86 nautical miles, NM, or approximately 8 statute miles, SM, which allows for more detailed information to be included on the chart. The charts provide an abundance of information, including airport data, navigational aids, airspace, and topography. This figure is an excerpt from the legend of a sectional chart. By referring to the chart legend, a pilot can interpret most of the information on the chart. A pilot should also check the chart for other legend information, which includes air traffic control frequencies and information on airspace. These charts are revised semi-annually, except for some areas outside the conterminous United States, where they are revised annually. VFR terminal area charts are helpful when flying in or near Class B airspace. They have a scale of 1 to 250,000. 1 inch equals 3.43 nautical miles, or approximately 4 statute miles. These charts provide a more detailed display of topographical information and are revised semi-annually, except for several Alaskan and Caribbean charts. World aeronautical charts are designed to provide a standard series of aeronautical charts covering land areas of the world, at a size and scale convenient for navigation by moderate-speed aircraft. They are produced at a scale of 1 to 1 million. 1 inch equals 13.7 nautical miles, or approximately 16 statute miles. These charts are similar to sectional charts, and the symbols are the same, except there is less detail due to the smaller scale. These charts are revised annually, except several Alaskan charts and the Mexican-Caribbean charts, which are revised every 2 years. Latitude and longitude. The equator is an imaginary circle equidistant from the poles of the Earth. Circles parallel to the equator, lines running east and west, are parallels of latitude. They are used to measure degrees of latitude north or south of the equator. The angular distance from the equator to the pole is 1/4 of a circle, or 90 degrees. The 48 conterminous states of the United States are located between 25 degrees and 49 degrees north latitude. The arrows in this figure labeled latitude point to lines of latitude. Meridians of longitude are drawn from the North Pole to the South Pole and are at right angles to the equator. The prime meridian, which passes through Greenwich, England, is used as the zero line from which measurements are made in degrees east and west to 180 degrees. The 48 conterminous states of the United States are between 67 degrees and 125 degrees west longitude. The arrows in this figure labeled longitude point to lines of longitude. Any specific geographical point can be located by reference to its longitude and latitude. Washington, D.C., for example, is approximately 39 degrees north latitude, 77 degrees west longitude. The meridians are also useful for designating time zones. A day is defined as the time required for the Earth to make one complete rotation of 360 degrees. Since the day is divided into 24 hours, the Earth revolves at the rate of 15 degrees an hour. Noon is the time when the sun is directly above a meridian. To the west of that meridian is morning, to the east is afternoon. The standard practice is to establish a time zone for each 15 degrees of longitude. This makes a difference of exactly 1 hour between each zone. In the United States, there are 4 time zones. The time zones are Eastern, Central, Mountain, and Pacific. The dividing lines are somewhat irregular because communities near the boundaries often find it more convenient to use time designations of neighboring communities or trade centers. This figure shows the time zones in the United States. When the sun is directly above the 90th meridian, it is noon Central Standard Time. At the same time, it is 1 p.m. Eastern Standard Time, 11 a.m. Mountain Standard Time, and 10 a.m. Pacific Standard Time. When daylight savings time is in effect, generally between the second Sunday in March and the first Sunday in November, the sun is directly above the 75th meridian at noon Central Daylight Time. These time zone differences must be taken into account during long flights eastward, especially if the flight must be completed before dark. Remember, an hour is lost when flying eastward from one time zone to another, or perhaps even when flying from the western edge to the eastern edge of the same time zone. Determine the time of sunset at the destination by consulting the flight service stations, AFSS, FSS, or National Weather Service, NWS, and take this into account when planning an eastbound flight. In most aviation operations, time is expressed in terms of the 24-hour clock. ATC instructions, weather reports and broadcasts, and estimated times of arrival are all based on this system. For example, 9 a.m. is expressed as 0900, 1 p.m. is 1300, and 10 p.m. is 2200. Because a pilot may cross several time zones during a flight, a standard time system has been adopted. It is called Universal Coordinated Time, UTC, and is often referred to as Zulu time. UTC is the time at the 0-degree line of longitude, which passes through Greenwich, England. All of the time zones around the world are based on this reference. To convert to this time, a pilot should do the following. Eastern Standard Time, add 5 hours. Central Standard Time, add 6 hours. Mountain Standard Time, add 7 hours. Pacific Standard Time, add 8 hours. For daylight savings time, 1 hour should be subtracted from the calculated times. Measurement of direction. By using the meridians, direction from one point to another can be measured in degrees in a clockwise direction from true north. To indicate a course to be followed in flight, draw a line on the chart from the point of departure to the destination and measure the angle which this line forms with a meridian. Direction is expressed in degrees as shown by the compass rose. Because meridians converge toward the poles, course measurement should be taken at a meridian near the midpoint of the course rather than at the point of departure. The course measured on the chart is known as the true course. This is the direction measured by reference to a meridian or true north. It is the direction of intended flight as measured in degrees clockwise from true north. As shown in the figure, the direction from A to B would be a true course of 065 degrees, whereas the return trip, called the reciprocal, would be a true course of 245 degrees. The true heading, TH, is the direction in which the nose of the aircraft points during a flight when measured in degrees clockwise from true north. Usually, it is necessary to head the aircraft in a direction slightly different from the true course to offset the effect of wind. Consequently, numerical value of the true heading may not correspond with that of the true course. To use a compass accurately, however, corrections must be made for magnetic variation and compass deviation. Variation. Variation is the angle between true north and magnetic north. It is expressed as east variation or west variation, depending on whether magnetic north is to the east or west of true north. The North Magnetic Pole is located close to 71 degrees north latitude, 96 degrees west longitude, and is about 1,300 miles from the geographic or true North Pole, as indicated in this figure. If the Earth were uniformly magnetized, the compass needle would point toward the magnetic north, in which case the variation between true north, as shown by the geographical meridians, and magnetic north, as shown by the magnetic meridians, could be measured at any intersection of the meridians. Actually, the Earth is not uniformly magnetized. In the United States, the needle usually points in the general direction of the magnetic pole, but it may vary in certain geographical localities by many degrees. Consequently, the exact amount of variation at thousands of selected locations in the United States has been carefully determined. The amount and the direction of variation, which change slightly from time to time, are shown on most aeronautical charts as broken magenta lines, called isogonic lines, which connect points of equal magnetic variation. An isogonic chart is shown here. Minor bends and turns in the isogonic and agonic lines are caused by unusual geological conditions affecting magnetic forces in these areas. On the west coast of the United States, the compass needle points to the east of true north. On the east coast, the compass needle points to the west of true north. 0-degree variation exists on the agonic line, where magnetic north and true north coincide. Because courses are measured in reference to geographical meridians which point toward true north, and these courses are maintained by reference to the compass, which points along a magnetic meridian in the general direction of magnetic north, the true direction must be converted into magnetic direction for the purpose of flight. This conversion is made by adding or subtracting the variation, which is indicated by the nearest isogonic line on the chart. For example, a line drawn between 2 points on a chart is called a true course, as it is measured from true north. However, flying this course off the magnetic compass would not provide an accurate course between the 2 points, due to 3 elements that must be considered. The first is magnetic variation, the second is compass deviation, and the third is wind correction. All 3 must be considered for accurate navigation. Magnetic deviation. Because each aircraft has its own internal effect upon the onboard compass systems from its own localized magnetic influencers, the pilot must add or subtract these influencers based upon the direction he or she is flying. The application of deviation, taken from a compass deviation card, compensates the magnetic course unique to that aircraft's compass system, as affected by localized magnetic influencers, and it now becomes the compass course. Therefore, the compass course, when followed, in a no-wind condition, takes the aircraft from point A to point B, even though the aircraft heading may not match the original course line drawn on the chart. Remember, if variation is west, add. If east, subtract. One method for remembering whether to add or subtract variation is the phrase east is least, subtract, and west is best, add. The deviation is different for each aircraft, and it also may vary for different headings in the same aircraft. For instance, if magnetism in the engine attracts the north end of the compass, there would be no effect when the plane is on a heading of magnetic north. On easterly or westerly headings, however, the compass indications would be in error as shown in the figure. Magnetic attraction can come from many other parts of the aircraft. The assumption of attraction in the engine is merely used for the purpose of illustration. A deviation card is mounted near the compass, showing the addition or subtraction required to correct for deviation on various headings, usually at intervals of 30 degrees. For intermediate readings, the pilot should be able to interpolate mentally with sufficient accuracy. For example, if the pilot needed the correction for 195 degrees and noted the correction for 180 degrees to be 0 degrees and for 210 degrees to be plus 2 degrees, it could be assumed that the correction for 195 degrees would be plus 1 degree. The magnetic heading, when corrected for deviation, is known as compass heading. Effect of wind. The preceding discussion explained how to measure a true course on the aeronautical chart and how to make corrections for variation and deviation. But one important factor has not been considered: wind. As discussed in the study of the atmosphere, wind is a mass of air moving over the surface of the Earth in a definite direction. When the wind is blowing from the north at 25 knots, it simply means that air is moving southward over the Earth's surface at the rate of 25 nautical miles in 1 hour. Under these conditions, any inert object free from contact with the Earth is carried 25 nautical miles southward in 1 hour. This effect becomes apparent when such things as clouds, dust, and toy balloons are observed being blown along by the wind. Obviously, an aircraft flying within the moving mass of air is similarly affected. As shown in the figure, an aircraft flying eastward at an airspeed of 120 knots in still air has a ground speed exactly the same, 120 knots. If the mass of air is moving eastward at 20 knots, the airspeed of the aircraft is not affected, but the progress of the aircraft over the ground is 120 plus 20, or a ground speed of 140 knots. On the other hand, if the mass of air is moving westward at 20 knots, the airspeed of the aircraft remains the same, but ground speed becomes 120 minus 20, or 100 knots. Assuming no correction is made for wind effect, if an aircraft is heading eastward at 120 knots and the air mass moving southward at 20 knots, the aircraft at the end of 1 hour is almost 120 miles east of its point of departure because of its progress through the air. It is 20 miles south because of the motion of the air. Under these circumstances, the airspeed remains 120 knots, but the ground speed is determined by combining the movement of the aircraft with that of the air mass. GS can be measured as the distance from the point of departure to the position of the aircraft at the end of 1 hour. The GS can be computed by the time required to fly between 2 points a known distance apart. The direction in which the aircraft is pointing as it flies is heading. Its actual path over the ground, which is a combination of the motion of the aircraft and the motion of the air, is its track. The angle between the heading and the track is drift angle. If the aircraft heading coincides with the true course and the wind is blowing from the left, the track does not coincide with the true course. The wind causes the aircraft to drift to the right, so the track falls to the right of the desired course or true course. The following method is used by many pilots to determine compass heading. After the true course, TC, is measured and wind correction applied, resulting in a true heading, TH, the sequence TH plus or minus variation, V, equals magnetic heading, MH, plus or minus deviation, D, equals compass heading, CH, is followed to arrive at a compass heading. By determining the amount of drift, the pilot can counteract the effect of the wind and make the track of the aircraft coincide with the desired course. If the mass of air is moving across the course from the left, the aircraft drifts to the right, and a correction must be made by heading the aircraft sufficiently to the left to offset this drift. To state in another way, if the wind is from the left, the correction is made by pointing the aircraft to the left a certain number of degrees, therefore correcting for wind drift. This is the wind correction angle and is expressed in terms of degrees right or left of the true course. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.